All right, so before we fit a model, there are a couple things that we need to think about. The first thing is you need to understand the content matter at hand. And so as a statistician, I often collaborate with subject matter experts to ensure that I understand the context of the problem at hand. And this is really important to sort of understand the bigger picture, kind of what the biological mechanisms might be, if this is like a medical question, it just helps with sort of getting better context for the whole picture. And this is a really important first step. And once you understand the content matter or the context, the next thing that's very important is that you understand the objective. And so it's really important to understand what the main objective is. What is the thing that you're trying to estimate? And ideally, these objectives are set a priori, or basically before you look at the data or start to fit a model. There are times when exploratory analyses are appropriate. Sometimes these can get deemed as fishing expeditions, but there are times when that's explicitly said that is the goal at hand. But when this is the case, it's really important that it's explicit at the beginning and it's also explicit at the end when you're reporting the results. You never want to go into an analysis where you're kind of digging for different answers. You come up with something and then you report it as if that was the goal all along. That's how you can end up with really kind of messy results. The next important piece is to understand where the data came from. And so this kind of falls into the same category as kind of understanding the content matter. But there's also kind of added pieces, things that are components of data that are really important to investigate. For example, was this data observational or was it experimental data? I think I mentioned in my introduction that I do a lot of studies that are purely observational, which means that the data was already existed in some context without the goal to answer a specific question. And it's important that when I'm working with this data that I know that that's the case, because there are things that you need to do when you're working with a data set like that, because it's a little bit harder when you don't have data that was specifically designed to answer a specific question. And that's in opposition to something like experimental data, where there's an explicit design and goal behind the data, even being at the collection phase. And the next important piece when you're thinking about where the data came from is there any missing data? So you want to make sure that you're tracking, were there systematic reasons why people didn't answer certain questions? Or maybe is there some reason why we don't have information about certain people in this data set? What are the units? And so what units are these different things measured on? Are there data entry issues? These are all really important data checks that you want to make sure you understand before you get to the model fitting step. The next thing that's important to do before you fit the model is getting the data into a tidy, analyzable form. And so part of this is once you've figured out where the data come from, whether there's missing data, what the units are there data entry issues, once you've established those facts, you can then do something about them. And so often we get data in a form that's really not easily analyzable. In this class, we're actually going to be focusing on mostly statistical methodology once the data is in an analyzable format. But just because it's analyzable doesn't mean the analysis choice is obvious. And so it's important to sort of at least keep in mind that in the real world, when you encounter data in the wild, you're often going to have to take the extra step to actually tidy it and get it into a good format. You'll have to do things like make choices about what to do with missing data, what to do if there's a data entry problem, etc. And then the final step is determining the appropriate model. So before you can fit a model, you have to figure out if the one that you want to fit is appropriate for the data at hand. And so in this class, we're focusing on linear models, which is a specific class of regression models. And linear models are not always appropriate for every question or every data set. You need to examine your data to determine whether a linear model is a good choice. And so these are those steps, just to reiterate the 5 steps that you need to do before you fit a model. You need to understand the content matter, understand the objective, understand where the data came from, get the data into a tidy, analyzable form, and determine the appropriate model. So there's really a lot to do before we get to the part that this class is mostly focusing on, which is on actually fitting the linear model at hand. So how do you determine if a linear model is appropriate? Now, this should definitely be a review from previous classes, but just to make sure everyone's on the same page, the outcome variable y is continuous. So that's the first kind of important point when you're working with a linear model. You need to have a continuous outcome. So by continuous, I mean like a numerical outcome, something like blood pressure or miles per gallon. That's a continuous variable. The explanatory variables, so x, which are often denoted as x1 up to xp, those can take any form. So those can be either continuous or categorical. The observations must be independent. And so, for example, if you're doing something where you're measuring the same person multiple times, you need to be accounting for that in something different than just a regular linear model that we're going to be talking about today, because those observations would not be independent. So you need observations to be independent. The residuals need to be homoscedastic. So that means they need to have equal variance. That's opposed to heteroscedasticity. So it's a problem when you have heteroscedasticity or you have unequal variance in your residuals. The residuals need to be normally distributed, and the relationship between the residuals and y needs to be linear. So these are basically the big pieces, the important pieces for making sure that your linear model is appropriate. The ones we can easily check by looking at the data are whether the outcome y is continuous, and then some of these pieces that we can look at about the residuals after fitting a model, we can make sure that these assumptions hold. Or if they don't hold, that they don't change our results too dramatically. So what are linear models used for? Well, there are two main things linear models are used for. The first being prediction of future outcomes using specific predictors, and the second being assessing the relationship between explanatory variables and the response. So a lot of this class is really going to be focused on the theory behind these linear models, but I just wanted to give a little bit of context for kind of what we're doing here. When we can actually appropriately fit a linear model, what needs to happen before you even get to the step of thinking about fitting a model, and what we might use those models for in the long run.